Hello, everybody. Welcome to this 2CRSI and Western Digital webinar. Today, we are very excited to have a talk with our partner from Western Digital, and we will cover an exciting topic, which is the power of NVMe over Fabric. My name is Sébastien Germain. I'm in charge of global go-to-markets at 2CRSI Group, and I will be your moderator for today's session. If you have any questions, please ask them in the Q&A box, and we'll answer them at the end of the session or via email later on if we cannot answer them all today. Of course, as usual, this webinar is being recorded. We will send you the recording link after the session so we can watch it again at any time, and we post the replay on our social networks as usual. Now, I would like to introduce you to our speakers for today's session. We are honored to have with us Manfred Berger, Senior Manager Business Development at Western Digital. Manfred has an extensive experience of 40 years in test engineering, product management, and business development. With us today as well, from 2CRSI, David Boursin, Head of Product Storage Solutions. And David has 15 years of experience in semiconductor design, technical marketing, and product management. So without further ado, I hand it over to you, David. I guess you will open the floor for us today by presenting 2CRSI. So enjoy the webinar. Thank you.
Thanks, Sebastian. All right, so 2CRSI is a server manufacturing company providing expertise in information technologies and high-performance computing. Our DNA lies in conception and research and development, as well as consulting services. 2CRSI focuses on delivering high-performance, customized IT infrastructure, and we focus on delivering performance while optimizing the carbon footprint and operating costs for our customers. 2CRSI is headquartered in France and has multiple international locations covering our customers' needs across the world. With more than 350 collaborators spread across 21 offices and 6 manufacturing sites, we are able to cover our customers' needs locally and to reduce turnaround time. 2CRSI has the privilege to partner with top hardware manufacturers such as Western Digital, and we are very proud to propose Western Digital's storage solutions to our customers. With that note, I'll hand over to Manfred.
Thank you, David. First, a few words about Western Digital as well. So last quarter, we generated $4.1 billion in terms of revenue and $116 million in cash. In other words, that's $1.02 per share. We operated on a gross margin of 27.7%, which is not the profit going to the shareholders. This is the money that is spent into extensive research, sales, marketing, and other expenses. In terms of portfolio, we have a very long history of foundational innovations, actually going back to 1956 when the hard drive was invented. But more interesting recently is the introduction of flash as a system storage device through compact flash by SanDisk in 1988. SanDisk later turned into SanDisk, which is now part of Western Digital. Another key invention was the introduction of the magnetoresistive heads in 1991, which allowed us to grow storage density by 100% year on year. And a little later followed by multi-level cell, which led to the acceleration of NAND capacity, performance, and price reductions, which eventually had flash catch up with the hard disk drives, except for one parameter, which is cost per terabyte. I won't go through all these inventions. This is just to give you an overview of what our 14,000 individual patent portfolio yields in terms of relevant technology. One more to mention is the helium inside the hard disk drives to reduce power, enhance life expectancy, and so on, as well as 3D on the NAND side, continuing to grow density to the capacities we see today at attractive prices. And finally, I'll mention OpenFlex, which was introduced in 2018 by Western Digital, which is the technology we're going to cover in more detail today. Sorry, the system fell asleep. All that allows us to be vertically integrated. across the entire portfolio. So on the hard drive side, we do all the key components from the ground up, including the wafers, heads, media, and eventually the final device with its firmware. And the same is true for the NAND side, where we share a factory with a partner which produces about 50% of the world's NAND flash, which ends up in NAND chips as used in many phones and other applications, and also our own SSD products. Here's the entire portfolio, starting from the NAND chips with a number of consumer devices, cards, USB devices, and so on. And also more relevant for this talk, the enterprise portfolio. And within the enterprise portfolio, personally, I'm responsible for the JBOTs, or just a bunch of disk platforms, the storage servers, and OpenFlex. Taking a closer look at the OpenFlex family, here's a network attached NVMe platform called Data24. This is used in composable infrastructure environment where it serves as disaggregated storage to a number of clients. It connects to the user's network via 6 100 gigabit links, which are shared across 24 NVMe SSDs. And the box runs the so-called RoCE protocol, which stands for RDMA over Converged Ethernet. And RDMA stands for Remote Data Memory Access or Direct Memory Access, which means the data of the device appears in the RAM of the client with very limited CPU interaction, so very effective overall. The maximum capacity we can support with this box is 368 terabytes, all that in a 2U 19-inch form factor. A key parameter when picking a storage technology is, of course, cost per terabyte and performance, but that's not covered in this foil. What I'm demonstrating here is that when you compare the direct attach SAS JBOF to an OpenFlex Data24 or an OpenFlex E3000, you'll notice that from about 92 terabytes and above, the extra cost of the networking equipment is fully compensated, and you're actually more cost competitive than the direct attach SAS box. With that said, let's have a look at the device. The front, as you can tell, allows you to access and change the NVMe SSDs individually. They're hot swappable. The box has the typical status LEDs for power, fault, or other status activity. And the same is true for the SSDs. You see the two I/O modules with 300 gigabit Ethernet cards each, as well as the 1 gigabit management port, which is run via a separate network. You also see two independent PSUs, or power supply units, as you would expect from an enterprise class device. Inside, we're leveraging our latest NVMe, the SN840, which is a high performance device, as you can tell from its specifications. We support two endurance classes, 1 and 3 drive writes per day, and capacities up to 15.36 terabytes. In terms of read and write throughput, we're in the order of 3 gigabytes per second per device. And in terms of mixed IOPS, we cover about 500,000. The other key component inside the box is the Rapidflex network card, which has 100 gigabit bandwidth, or in other words, 4 25 gigabit lanes, which can be used with link aggregation. This is the card in charge of the RoCE protocol that I mentioned earlier, and it has a number of networking functions that guarantee a loss-free network by congestion, notification control, and so on. And in terms of NVMe devices sitting on the PCI Express bus, it supports version 1.2 and 1.3, as well as the application program interface to manage the namespaces and so on. But I'm covering that in a separate foil later on. The question we get asked most of the time is why we adopted the RoCE protocol. If you look at RoCE and TCP side by side, nothing really stands out except for two parameters. The average latency under RoCE is about half that of TCP. And even more relevant, the distribution of the command latency is much tighter. So TCP has about a 10 times wider command response distribution, which is not desirable in high performance compute application. In terms of sample use cases, there's a lot starting from genomic research over real-time analytics, video analytics, artificial intelligence, machine learning, and even online gaming. What all these have in common are requirements in terms of low latency, high IOPS, and high bandwidth. A few words about open composability. It all starts with disaggregation, which means you pull the individual technology resources from a server, you group them in independent pools, and later on, when you have to create a server in charge of a certain application, you withdraw components from these resource pools and synthesize or compose the server with just the resources needed for the task at hand. So very cost efficient as a concept overall. To explain some of the background, let me first show what computers are looking like today in terms of architecture. You have a CPU complex, you have a memory interface that the memory is attached to, and all the rest is connected via PCI Express lanes. Today, these are clocking at 10 gigabits each, just going to 20 with the version 4 introduction. By taking the PCI Express out, removing the NIC complex and integrating it into the CPU complex and adding Ethernet to all the remaining groups, you have a new architecture, which is now network-based. And for Ethernet, you must understand the individual lanes today are already at 25 gigabits per second, so even faster than PCI Express, with the roadmap going to even 50. So you gain flexibility, but you don't lose performance in doing that. With everything said so far, you have these logical pools that I mentioned before. And from these pools, you can pull individual slices to create any kind of system needed for a certain application. And that's then called composability. Comparing that to hyperconverged installations where you might have thousands of similarly equipped servers, you typically end up with a few resources that are underutilized. So in other words, you wasted your money, or they could be limited and overstressed with no way to solve it other than taking them out of service and upgrading them individually. But in the disaggregated approach, where you have pools of flash, network, and other compute resources, you are more agile because you don't have to actually touch the physical hardware. You're more efficient, and the whole concept is fully scalable. Looking at the cost of that, the total cost of ownership in the disaggregated approach is estimated to be 50% better, or 40% better. And the initial upfront investment, because you can scale as you go, typically is about 50% lower. And the best message of all, this is applicable to all compute environments, be they virtual, container-based, or just bare metal. Looking at how you would deploy Data24 in the simplest application is having a number of compute nodes connecting with parallel redundant links to the I/O modules that I showed before. And every server can then share about 8 NVMEs on the inside of the box. And 8 is more than you would typically fit in a general purpose server. So you gain capacity by leveraging Data24. But even more interesting is a scenario where you have an Ethernet switch between the clients and Data24, because now every client or server can address any namespace on the box. More elaborate and probably more typical in practical terms is if you have a storage cluster consisting of storage servers and metadata or management servers, leveraging multiple data 24s. There's a few examples here, BGFS, Linbit, or OS Nexus. And the nice thing about that is these servers or these software-defined storage packages can now add additional functionality. They can add mirroring, replication, erasure coding, thin provisioning, encryption, whatever you want. And the other nice side effect of that is you would not have to have RDMA-capable networks across the entire company. It would only be needed within the cluster for the reasons I mentioned before. And on the client side, you can leverage whatever is in place and whatever the storage servers support. So it can be Ethernet, InfiniBand, fiber channel, with or without RDMA. The API that I mentioned earlier running on the individual NICs is actually fairly simple. It shows you the resources available on the box. It shows you the resources already in use and the compound throughput of the box. And via this interface, you would create volumes on the NVMEs, or in NVMe specific terms, you would create namespaces, which carry a 16-byte identifier and then can be used by the clients on the other side of the network. And with this API, you decide whether a namespace is universally addressable by all clients, or whether it follows a fixed IP path, in other words, reserving it for an individual client. Here, an example about one of these software-defined storage packages that qualified OpenFlex. It is the Linstor software by the company called Linbit. In other words, this is a DRBD-based block storage, which functionalities, as I mentioned before, synchronous replication, asynchronous replication, and others. And since it's a block interface, it's about 6 times faster than object storage under Ceph. Linstor provides interfaces to container applications like Kubernetes, or OpenNebula and Proxmox and others. Completely different application that we tested with OpenFlex is the Minio object store. The target application of an object store is a storage device that has very robust data retention and is infinitely scalable. So typically would deal with large objects that you have to protect from any kind of possible hardware failure through erasure coding. Erasure coding comes with a lot of computation overhead. That's why this is not the fastest possible, but it's the most robust storage implementation you can have. What's mentioned here is a 12+4 erasure code protection, which means every object is sliced into 16 blocks, of which any four can get lost, and you still have full access to the data. In terms of read throughput, we achieved 24.3 gigabytes per second for 64 megabyte objects. And this is measured as get throughput, and get is the read function in the object storage world. In terms of writing, with all the erasure coding calculation going on top, we achieved 6.5 gigabytes per second in terms of put throughput. And important to mention, even modern container applications like Kubernetes are already leveraging an S3 interface for very robust storage. Not necessarily for performance, as I said, but definitely for robustness and long-term data retention. Another software-defined storage package we looked at is the OS Nexus QuantaStor 5, where we did a fairly small test configuration with a single switch and 1 to 6 storage servers. But even with that limited setup, we achieved almost 20 gigabytes per second read throughput, nearly 10 gigabytes per second write throughput. And in terms of 4 megabyte read-write IOPS, we came close to 1,500. A more typical installation in the field would consist of multiple OpenFlex units, a dedicated fabric switch for these, and then a server cluster of at least 6 with a dedicated cluster switch, and then also a dedicated client-side switch, which gives you a much better performance overall than we showed in our little test. And all that provides you storage services, either in terms of block storage, iSCSI or fiber channel based, scale-out NAS, which is a file-based service, which can be NFS or SMB, and also Ceph-based object storage, again, leveraging the S3 interface that I mentioned before. We've also done is to see how that scales with the number of servers. And because object storage involves a lot of calculation, as I mentioned, you see that the achievable throughput actually scales nicely with the number of cluster servers and eventually flattens beyond 6, where it reaches the performance limitation of the Data 24. With that, I covered all subjects we sorted for you today. If there are any questions, we're happy to take them. Thank you.
Right. Thanks,
Thank you. Yeah, David, sorry, you wanted to say something?
I just say thanks to Manfred.
Okay.
You're welcome.
Okay, thank you. So thank you to you two for this very interesting content. I see many questions popping up in my chat box. Maybe I propose you to take some of them. The first one, I don't know who wants to answer this one. What are the challenges of NVMe within existing hardware?
Yeah, let me start with the positive side. NVMe at low latency, very high throughput, cost-wise is very close to SATA. However, today's platforms are not always ready to receive NVMe devices, at least not ready to receive them in high numbers. And this is what we're addressing with Data 24, because we remove the NVMe from the server, accumulate them inside the Data 24, and then make them available across the network. The remaining challenge is you need an RDMA-capable network, which isn't in place in all cases. However, as I showed, there is a cost advantage versus SAS, and in a direct attach scenario, you really only need one RDMA-capable network card in your server, and then you can connect the Data 24 and leverage the NVMe. So there's a multi-staged approach, and sorry for the complexity of it all, but that's the fate of the IT manager of today, to deal with new technologies all the time. But as I showed, the implementation is actually not difficult and can be taken step by step.
Well, I'm certain that we answered the question perfectly well. So thank you, Manfred. Second one would be, is there a preferred capacity of SSD to take the most advantage of Data 24?
Yeah. So there is an overhead, of course. I mean, the 6 NICs don't come free, and whoever bought NICs individually will know what they'll cost. However, from about 92 terabytes, as I was showing in an earlier example, that cost is fully compensated. And if you grow towards larger capacities, you end up reaping more and more cost benefits.
Okay, thank you. Is there a possibility to request an evaluation of Data 24 and FPS? What are the requirements?
Yeah, so there's an ask on our side. Shipping hardware around, especially with the price ticket of a Data 24, is very costly and also time consuming. So the preferred approach actually is that customers that want to test the unit do so at our premise. We have the ability to make the unit addressable via TeamViewer, that is. So we would give access credentials to one of our servers. We can then install your kind of application and test the performance directly between the server and the unit. What we ask, other than what I just described, is that you come forward with a business case. Because if it's just about kicking the tires and confirming some of the numbers, we've already proven that doesn't make a lot of sense. But if you have an application and you want to test compatibility, then you're more than welcome to get in touch either through 2CSI, who has access to units as well, or directly with us.
Absolutely. Thank you. Maybe we can take a last question. Let me pick an interesting one. Which applications are to extract the most performance from data 24? And maybe you can give us a concrete example or indicate a case study in which the data 24 was used.
Yeah, I can't point to an actual customers because that would require a written agreement before I mention names here.
Yeah, true.
So we had applications in the medical field, but maybe one that stands out and resonates with a lot of people out there is where you have a large number of clients with mixed capacity and performance needs. And virtual Windows clients, for instance, could be such an installation. That's where you get the most out of it. And here are the two reasons for that. By moving the physical client SSD into the data 24, you gain a lot of burst performance because data 24 is based on enterprise class NVMe's, whereas the client might have been based on an M.2 SATA device. So you gain peak performance because you will see the burst performance of the enterprise class device. And you also gain robustness, right? A client SSD typically has very low drive writes per day, but the enterprise device on our side has 1 or 3 drive writes for the entire system or the entire NVMe. And even though a client may only use portion of the storage, it has the full robustness of the enterprise class device behind it, literally cranking out 100 times the write capability of the local client. So that's a most typical one. You see that in gaming, you see that in other applications. So for instance, we have customers in the finance world, which have thousands of clients hammering the same data set that they draw from the financial markets, doing analysis, trying to predict courses. So in short, sorry for talking so much.
Yeah, no problem.
Wherever you have a lot of clients wanting super robust performance or wanting to solve one problem, sharing one set of data, that's where we see the perfect scenario for OpenFlex devices.
Thank you very much, Manfred, and thank you for also for the interesting questions that were asked today. We are now reaching the end of the session. Thanks again, Manfred and David, for your time today. Thank you very much, everybody, for attending to this webinar. More webinars are coming from 2CSI and Western Digital, of course. Meanwhile, you can visit our digital touchpoints, websites, and social media. Please do not hesitate to follow us on LinkedIn and Twitter. And like I said, stay tuned for more webinars and, well, enjoy the rest of your day. And thanks again for connecting today. Thank you.
Thank you.
Thank you.
Thank you.